Hello friends, welcome to follow up. In this video, we look at another easy problem 2980. Check if bitwise OR has trailing zeros. As we mentioned in the previous video, this is the first day of the new year, so we practice some easy problems to start. So here in this video, we are going to do some simple practice on bitwise operations. So first we are going to digest the requirements and then we do the analysis and the coding. So the logic here is very simple, and then we are going to do it quick, and then we are going to do it quickly and get some variants of the solution. So first let's look at the problem statement. So here we are given an array of positive integers called nums. So we want to check if it's possible to select two or more elements in the array such that the bitwise OR of the selected items has at least one trailing zero in its binary representation. So here it gives some examples with numbers with trailing zero and not. So we want to return true if it's possible to select two or more elements with the above requirements. Otherwise, we are going to return false. So if you look at the three examples here, if you look at example 1, so for sure we can select number 2 and number 4. So those two numbers are powers of 2s, so the least significant bits are all zeros. So in their bitwise OR, we are going to result 0. So this return yields true. And in the second example, so all the numbers are powers of 2. So the least significant bit are all zeros. So you can choose any 2 or more elements from the list, right? So we return true. And in the third example, this is very special because all the numbers are odd numbers. So in other words, if you do integer division by 2, it will has remainder 1. In other words, the least significant bits for all these numbers are non-zero or 1. So in any bitwise OR, you're going to get 1. So we return false. So here the constraints are the following. First, the length of this nums is bounded below by 2. So this is due to the requirement that we need to select 2 or more elements. And it's bounded above by 100. And also the numbers are in between 1 and 100. So as we know, 2 to the power 7 actually is 128, right? So basically for all these numbers, we at most need the 8-bit positions or check 8-bit positions to get their binary representations. So that's basically a very small size problem. So now let's look at the main observation. So the main observation is that if the bitwise OR result of a subset of elements from the list nums has trailing zeros, then the least significant bit of all these selected elements, or the rightmost bit, must all zeros, right? So we just need to check that if such elements the number of such elements is greater than or equal to 2, or which element, the elements with least significant bit being 0, right? So, but how to check if the least significant bit of an integer is 0, right? So the answer is that we can check y bitwise add operation with 1. So if y bitwise add with 1 is 0, it means that the least significant bit is 0. Otherwise, it's 1. So in general, so if we want to check if the ith bit of an integer y is set or not, we can check y integer division by 2 to the power 2, and then bitwise with against 1, right? So you can write this one in this format, y a bit shift to the right by ith position, right? So then we against 1. If the result is 1, it means the ith bit is set, otherwise not, right? So equivalently, you can check this, y and with 2 to the power I, right? So in this case, you need to check if it equals 2 to the power I or not, right? If it equals, it means that ith bit is set, otherwise not. So with that said, actually, that's the main knowledge we need in solving this problem. So first, actually, we want to write a one-line solution. So we just need to check. So here we can use comprehension. So we want to check if the element has a least significant bit to be 0. So in this case, we want to check if this condition is true. The true corresponding to 1, right? So we just sum all these expressions for y in nums. So this is, counts the number of elements with least significant bit being 0. So we want to verify if it's greater than or equal to 2, right? So this is the one-line solution. Let's do a quick test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. However, if you look at a little bit closely at this problem, here we checked all the list. This is actually not optimal. So let me copy this function signature, and then we write another solution. So here I'm going to use v1, and then we're going to use some stop condition. Let's see, we use the count to be 0. So we're going to count how many numbers in nums list has least significant bit being 0, right? Then basically for y in nums, so if y and 1 is 0, then we're going to increment the count by 1, right? So once the count is 2, so we can return true already. So this will automatically stop, jump out of this for loop. Otherwise, if nothing has returned, we are going to return false. So this is another solution format, because it looks like a early stopping. Let's do a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So in this problem, you can also put this check here, right? Because if it's not 0, we didn't actually update the count. So you can test. So this is another solution. So here, basically, we use this operation, which might be not very beginner friendly. So now let me copy this part. I will write a much more beginner friendly one. So here, if you do not want to check this, you can check if, so modulo 2, if it's 0, we can do this, right? Otherwise, we just check. So you can do this and test. This might be beginner friendly, right? So here, this is also the first step, to get binary representation for a number. So for example, you can write some quick method. Let's see, check to binary. Let's see. So let's add as a method in this solution. So here you have number, right? And let's assume n is greater than 0, integer, right? So here in this problem, it assumes, so it's greater than 1. So here we can get an integer list, right? So see, well, n is greater than 0. So what we're going to do? So we're going to do result. So let's see, qr equals def mode. So n integer divided by 2. So here we can automatically set this quotient to be n, right? Update this one. Then we're going to result append this r, right? So we're going to return this result. So this result will give a binary representation of this n, but in a reversed order. So in practice, you can see actually reverse that if you like, or you just not use append, but add this at the very beginning. So here we can do a test. For example, let's see, print self to binary. So let's check see 7, 5. 5 is 101, right? So let's see what we get. It's running slow. I don't know why. Yeah, so let's so here we need to put it, so because this is the version we want, so we need to put it here. Let me delete this part. Yeah, so your concatenate is 101, but if you concatenate all this or translate those numbers into string, you're going to get the standard binary representation. So let me check another one. Let's say 8, and it will give us 1000, right? Let's test that. Right. So basically, this one is corresponding to the first step, right? When you do the while loop for translating an integer into binary representation. So with that said, I guess we explore this problem in a, to an extent that is sufficient enough to digest the requirements and the corresponding knowledge point. So with that said, I guess that's it for this video. Thank you.